Assalamu alaikum students, I'm your course instructor Muhammad Kashif and the course name is Design and Analysis of Algorithm. In previous lecture we have covered an algorithm that was Dijkstra algorithm, and you have seen that in Dijkstra algorithm we explore or we solve a problem related to the graph theory in which we have undirected graph, and you have seen that we find out a shortest distance while exploring all the nodes. And obviously this is the plus point of this algorithm, because when we implement graph, when we use graph to solve our real life problems, we need to find a shortest distance while we are traveling, or whether we are moving from one place to another place, or we are sending files from one computer to another computer. So this algorithm or this theory can be used to solve these type of problems where we need to find the shortest, or where we want to pay a minimum cost to send or receive a file. So Dijkstra algorithm helps you to find the shortest distance. It helps to find those paths which has minimum cost. And obviously if we have weight and if we have cost on each edge that connect multiple nodes, that allow communication, data communication between communicating devices, or between nodes, or you can say the mobile devices. So we have to find a solution, we have to find a way which can give us, or which can return, a shortest path. So we explore this algorithm in our previous lecture, how we can find the shortest, or how we can find the best solution to solve our problem. In today's lecture we are going to explore in another way, and that is basically a directed graph, and we will see how Dijkstra algorithm works on directed graph. And obviously we will discover, or we will explore how it works on on negative edges, and we will explore the drawbacks of Dijkstra algorithm, how it responds you when we have a negative edge in our graph. And negative edge means if we have weights and they have values in negative, so how it will treat, how it would work on that particular negative edge. So and definitely if we are talking about directed graph, that means we are bounding a user, or we are bounding to a computer node to follow that particular direction. So when we have directed graph, that means we have constraints, we have limitations to allow a user to, or allow a computer to communicate in that particular direction. But when we have constraints, or we have limitations, that means we have some trade-offs. Trade-off means maybe we can get the best solution, or maybe not, because when we have a limited scope, when we have a particular direction, then maybe there might be chances to pay more cost, then, or maybe we can pay a less cost. So let's see how it works on directed graph, and how it will produce a solution or a path that can be used to implement your problems. So students, we are going to assume an example that can help to solve our directed graph problems, and for that we have to assume some nodes, and the nodes are like A, B and D, and we have node C, and we have node E, right? So obviously we have to establish connections, or we have to mark the edges between these nodes. So here you can see that we have a directed graph in each node, and you can see we have directions available. That means we have to follow these paths. So when we talk about the directed graph, that means we have some limitations, we have some constraints from the system, and obviously we have to follow these directions. And one more important thing, because we are trying to find the shortest path, so if we do not have weights on each edge, then we are not able to find the shortest path. So as you can see that we have weights on each edge, and based on these values we are going to find the shortest path. So this is a directed graph and we are going to use Dijkstra algorithm to explore all these nodes. So I'm going to write a matrix for this particular problem, and we have a solution in a way where we can use a matrix to represent our nodes in a fashion or in a manner that represents the adjacency, but adjacency would be according to the direction. So as you can see that we have 5 nodes in this graph, A, B, C, D, E. So I'm writing in this way, A, B, C, D and E. Why I start from A? Because I'm assuming that I have a root node, that is A, and I told you in previous lecture we have to decide, or we have to identify the root node. So root node could be B, or it maybe we can start from D, or it could be either E, or we can start from C. So you can choose any one of the node to start traversing, to start your algorithm. So I am using A as a root node, right? So obviously if you are using A as a root node, then you have to write A first, and rest of the variables, or you can say the nodes, would be placed like this. And if you are using root C as a, if you are using C node as a root node, then you have to mention, or you have to start from C, and the rest of the nodes would be like this: A, B and D or E. So if I'm just talking you and I'm just telling you, if we have a starting node, or if we are starting from a node, any node that could be placed on a first location. So this is the algorithm, or you can say this is the method to represent the table for directed graph. So here the same thing that we are going to do here, and that is, first of all, because we are starting from A, so we are going to place the cost, that is 0, against this node, or you can say we are going to place cost 0 at this node, right? Now we are mark the cost at each node, that is infinity, because computer doesn't know about the updated cost, or you can say the actual cost at each node. So we just try to find these updated cost after running the Dijkstra algorithm. So as you can see that only A node has a cost, that is 0, and the rest of the nodes have cost infinite, right? So now according to this situation, we are going to update our table. We are going to update these values, because at this point we have 0 and we have infinite values on rest of the nodes, right? So I am going to explore this graph by using Dijkstra algorithm. So as you can see here, our source node, or our selected nodes, you can say selected, or you can use a word visited, right? Any naming convention you can use for your algorithm. So this column is basically represent the visited nodes, or you can say the selected nodes. So here we are going to select a node, and we select this node as a the root node, and I'm going to mark this as a selected, because this is the minimum value if I compare with all the infinite values, right? So I'm going to start from 0. And you can see here we can move from A to B or A to C, because direction gives us an idea of movement of data, because direction gives you the direction allow you to move from one node to another node. Obviously we have connection between A and E, but direction is basically from E to A, so we cannot move from A towards E, right? So we can only move from A to B and A to C, right? So if we are moving from A to B, then definitely we are going to use some variables, and variables are like U and V. And as you know the algorithm or the formula, and that was like, if we have D of U and we have cost of U comma V, right? And that should be less than D of V. D of V means if we are if we are accessing B node from A, that means this is your destination and this is the variable name V, right? So the updated cost should be less than infinite, that and we already discussed in our previous lecture. So if we have got the less than this value, then definitely we will update, else we will not update. Do not update. This was the algorithm that we used in previous lecture, right? So here we are going to access B via A, right? So we are here and we have selected a node that is A, right? Because we mark this node as selected node, or you can say the visited node. So we are not going to mark here right now, because we just check what cost we will get to access B from A. So if we move from A to B, then you can see that we have 0 plus 10. So 0 plus 10, that is equal to 10, and 10 is basically less than infinite value. So we are going to update this value here. 10 is less than infinite, so we are cancel out this infinity and we are updating this value. And you can see here we need to update this value in table as well. So we are moving from A to B, and B, what we have got here, we've got 10. So 10 is basically less than infinity, right? So we update this value against B, right? And where we can move from A, we can move towards C, because direction allow us to move from A to C. So what cost would you get after accessing this node? So 0 plus 5, 0 plus 5 equals to 5, and 5 is basically less than infinite, right? So we are going to update this value as well, and obviously we are going to update in table as well, because 5 is less than infinite, right? Because we can access B and C with A. So you can see that we are updating the values on a particular row and column, and that particular row and column represents the node B and represents the node C. So rest of the nodes are the same, because we are not accessing D and E from A, right? So the same values will be the same values would be replicated in next row. So now here we are going to check, we are going to mark this node as visited, because all the adjacent nodes have been explored, or you can say all the nodes have been updated with their latest cost. So we have marked this node as visited, right? Because this table shows, because we select A as a root node and we traverse from A towards B and towards C. Right now here we have to check what value is basically less than all other values. So we can see that 5 is basically minimum than 10 and infinite values, obviously. So we are going to highlight this value, because we choose this node as a source node. So that means we are moving towards C, right? So here I'm going to mark this node, because we reach out to this node. Now we can see here we have selected C node, so we are going to write this node at this column, because this value represents the C column, and here we actually updating our visited or selected nodes, right? So I'm going to mark this node as visited, right? We can mark this node in the early stage, because obviously we are exploring further more new nodes via this node. So that means we will end up this node after exploring all the nodes. So here you can see that we can move towards B, we can move towards D, and we can move towards E from C, right? So what values we can achieve from C to D, C to B, and C to E? Right, if we see that we can move from C to C to E, and if we move from C to E, what we will achieve? We will achieve 7, because 5 plus 2 is equal to 7, and 7 is basically less than infinity. So we are going to update this value. We are going to update it in graph as well. So we are going to update this value here, right? So here we've got 7, and now we are checking this path. So 5 plus 9 is basically 14, that is less than infinite value, right? So we are going to update this value as well. So here we need to update in a table value because we miss this value on this edge. So if we add 5 plus 3, that would equal to 8, right? So 8 is basically less than 10. So we are going to update here, right, with 8. So what we have got 3 values by accessing by this node, because we are moving from C to B, we are moving from C to D, and we can access node E by this node, and we reflect all these values in this particular row. And you have seen that we are not going to update here because we already select this node. We have already been select this node, so we are not going to update here because we already choose these values. So you can see that we are not updating on this particular column, and we are not going to update this column because these values or these nodes have been already selected. Now here we have to decide what value is basically shorter, or what node has basically the minimum value. And if we compare all these values, 7, 14 and 8, what is the minimum value? We can see that 7 is basically the shorter value or the minimum value. Now we are going to select this node as a the source node. So we are going to mark this node as selected, right? So here we have selected the node E, right? So we are going to write E over here. Now the direction would be like this, because we are moving towards E, right? So our direction would be like this. We are here and we can explore, or we can visit the adjacent node that are connected with E, or you can say the E is basically the source node for those nodes or those devices which can be communicated from the E node. So as you can see that we can move from E to D and we can move towards A, but A is already marked as visited, right? So we are not going to explore, or we are not going to access this node. So we can only access the D node, or we can update this D node if we get the minimum value than the 14. And if we move from E to D, we can see that at E node we have 7 and the edge cost is basically 6. So 7 plus 6 is basically 13. That is minimum, or that is less than 14. So we are going to update this value. That means we are going to update in a table as well. So we update 13 instead of 14. We are going to write 13 instead of 14. So that means the value has been changed here, right? So now obviously this node has been selected, and these two nodes have been left, and these are the remaining values. 14 has been updated as 13, and this node is not visited yet. So we are going to copy this value as it is in our next row, right? So what we have at this position, we have two values, 13 and 8. So E has been marked as visited because we explore all the adjacent, or the connected nodes, and we update these values in our table, right? So what we are going to do here, we are going to again check or compare what is the minimum value. So as you can see there, 8 and 13, if we compare both the values, we will find a minimum value, that is 8. So 8 is basically has been selected now. So here we have select 8, that means we are talking about the B column. We are selecting B node. Here we have write the node B because we choose this node to traverse furthermore. So here we are trying to access from B to D, and obviously there is only one node that we can explore, or you can say we can visit from B. Obviously direction allow us to move from B to D only. We cannot move from B to C or B to A, right? So now we have to check what value we will get after accessing the node D by B, right? So the U is basically 8 and the cost of this edge is 1. So 8 plus 1 equals to 9. So here we are going to update this value again. So because 9 is less than 13, so here we have updated this value, and we will update this value in a table as well, right? Because we update the value against D node, right? So here we explore all the nodes in our table except this node. So obviously there is no other value than this 9, so we are going to select this node, and obviously we have to update our column that is called selected column, right? So here we have selected 9, and 9 is available on a column that is called D, so here we are going to select D. So here if we try to access from D to any node, then we can see that we cannot move from D to any node because all the edges are pointing towards D. We are not use D as a source node, right, as you can see here. So that means we cannot explore further more nodes. So D has been marked as, visited node. So all the nodes have been explored, and you can see here in a graph all the nodes have been marked as visited. So what we have got? We have got a path, we have got a direction that is A, C, E, B, D, right? So here we cannot say that we end up with this topic. We just find the shortest path if we want to access A to D. Let's say if I talk about I want to move from A to D, what path should I follow, or what should be the path, shortest path that I can use to access from A to D? And obviously I want to move from A to D, and here I can see if I want to access the node D, that would cost me 9, right? That means to access node D from any node I have to pay the cost 9, right? That means I want to tell, or I want to find that particular path that return me the value that would be equal to 9. So here I'm going to write a path, or I need to find that path. So I'm going to point out this node because I'm starting from D, and if I move back, if I move upward, and the pointer would be here. Here we have updated the value, we have changed the values. So just keep in your mind, whenever we try to explore or we need to find the path, then we have to look into the table, and we have to do a backtracking in our table, because we are at here, we want to access node D from A. So definitely we want to start from D node, and then I want to move upward. And when I move upward, then I have to check whether the value has been changed or not. And if the value is changed, then definitely I have to check what node was there, what value we have selected, right? So value has been changed, so here we used B to traverse here, right? So that means we start from D and we move towards B because we selected this node as a source node. So right, I'm going to write the B as a source node. Now obviously the both values has been checked. Now I'm going to move upward, and when I move upward, then I will see here this value was not updated, or this value was not changed, right? So that means I'm not going to update my value. I'm not going to use the values over here. So here I am going to upward, and when I move upward, I can see here I have changed the value, and I told you when the value has been changed or value has been updated, then I have to check, or I have to see what node I was selected. So here I selected node C. So here I want to update the node here, that is C, right? So now the node has been chosen, node has been selected, so I am going to upward, and when I move upward, you can see here the value has been changed because there was 0 selected as a source node, right? So when I move upward, the value was changed, value was updated, so I am going to select A as a source node. And now I want to rearrange, or I have to rearrange this value A, C, B and D. And if I use the value of edges that is available between these nodes, I can see here if I move from A to C, C to B and C to B to D. So the path would be like this. If I move from A to C, C to B and B to D, then what would be the cost? 5 plus 3 plus 1, that is equal to 9. So if I add up all the values that are available on the edges, 5 plus 3 plus 1, that is equal to 9, and actual cost was 9 to approach the D. So this is the shortest path to access the node D from A. So we can access any node from any other node, right? So this is the only way, or this is the only process to access a particular node by paying a limit or by paying a minimum cost, right? And Dijkstra algorithm gives you a shortest path, and we find the shortest path on each node, right? You can use any direction, or you can choose any node to approaches or access any node, then you will find a shortest path, you will find a minimum cost. Now let's talk about the other aspect, what happen or what will perform our Dijkstra algorithm on a negative edge, or when we have a graph where we have a negative edge, then how it works, how the algorithm perform on that particular example. So obviously we are talking about the drawback, or we will see how it works. So for this particular example, or you can say the negative edge, if we have negative edge in our graph, negative link, or you can say the drawback of Dijkstra algorithm, drawback, right? Then we have to assume an example, and we have for this particular situation, we have to make a graph in that manner which has the negative edge, and we have to check what will happen in this particular situation. And you can see here I am marking, or I am using the edges that has direction, and obviously these edges have some cost, and that is, let's say if I use 5, if I use 10 here, 1, and here I'm going to use a negative value. So this is a negative edge, right? So first of all, I'm talking about this negative link, and then I will tell you the drawback, what will happen after applying the Dijkstra algorithm on this particular situation. So obviously the mechanism is same. We have to select our root node, and this is our root node. So rest of the nodes are infinite, right? So I'm marking infinite on my rest of the nodes. So if I'm starting from 1, then obviously I can use 2 direction. I can move from 1 towards 2. I can access node 3 from 1, right? So if I use to explore 2 by using this node, then I can see here 0 plus 5 equals to 5, and 5 is basically less than infinity, so I'm going to update this value. And I can move from 1 to 3, that means I can update 0 plus 10, that is equal to 10, and 10 is basically less than infinity, so I'm going to update this value here. So 1 has been marked as visited. So now I need to check what node has minimum value. Obviously I need to compare 10, 5 and infinite values. So 5, 10 and infinite values, which one has smaller value? Obviously 5. So when I move towards 5, that means I'm here, and you can see here there is a deadlock, because I cannot move from this node to any other node, because this node is not used as a source node. So obviously 2 cannot communicate with anyone else, right? 2 can accept the data, but 2 cannot send the data, right? So we cannot update this value here, because we have a situation where we cannot move from 2 towards anyone else, right? So we are going to mark this node as visited. So now this data has been marked, or you can say this value has been discarded from the competition. Now we have 10 and infinite. Which one is minimum? Obviously 10. Now we are going to explore adjacent node of 3. So we can move only from 3 towards 4. So, and we cannot go back towards 1. So if we move from 3 to 4, then we have value that is 10 plus 1, and that is equal to 11. 11 is basically less than infinite, so I'm going to update this value. 11 is less than infinity, right? So I updated this value. So all the adjacent nodes have been explored now, so I'm going to mark this node as visited. Now here I can see I can move from 4 towards 2, but 2 was already marked as visited. Logically, it's not a correct way to move from 4 to 2, but you can see if I try to move from 4 towards 2, then 4 has value 11 and the edge has cost that is minus 10. And if I add both the values 11 minus 10, that is equal to 1, right? So 1 is basically less than 5. So here you can see if I want to access from 4 towards 2, so logically it's not possible, but if I try to access this node from 4, so I want to add these two values. 4 minus 10, that would be equal to 1. So it actually gives you, or it return you a minimum value, because 1 is less than 5. So I want to remove this 5 from 1, but I cannot do that. So this is the drawback, because I'm getting the shortest path by if I'm using the direction, if I'm using this situation to access or to update the value, but I cannot update this 1 with 5, because Dijkstra algorithm not allow to visit or mark those nodes which are already marked or visited. So this is the drawback. Because it may or may not, because it may and may not provide you a better solution when you have a negative edge, right? So this was the situation, or this was the drawback that I was talking about. How the Dijkstra algorithm gives you, or it might be or might not be allowed to use a shortest path while you have a negative edge. And if let's say if I have a negative edge and that is basically minus 1, so what will happen if the value is minus 1? Then 11 minus 1 equals to 10. So 10 is basically that is not less than 5, so we are not going to update. So there is a specific situation where the Dijkstra algorithm may or may not perform in your negative edge. So this is all about today's lecture that we discussed about the Dijkstra algorithm performance on directed graph and on a negative edge. And we have seen that how Dijkstra algorithm works on directed graph. And in a directed graph, we used a matrix where we updated our nodes. We represent our nodes in the form of rows and columns, and definitely there must be values of edges, and we updated all the edge values according to the directions or according to the situation. And obviously we have adjacency list, and based on that adjacency list we are going to update all the adjacent nodes, and we update the values in a table. And we have a specific situation, we have a case where Dijkstra algorithm may not perform well, because you have seen we used a negative edge in our graph where Dijkstra algorithm can perform better, but that was the situation where our shortest path was not derived, right? So that was not the exact, or that was not the acquired solution that we want, right? So in a negative edge, Dijkstra algorithm may or may not perform or give you a shortest path. So this is all about today's lecture. If you have any question, you can ask to me. Thank you so much.